Welcome to Innovate and React. Today's episode will be about how catalysis can be used for water treatment and possibly reduce pollution from shipping. I'm very happy to welcome Janek Betting to the show, who is currently doing a PhD in catalysis at the University of Twente in the Netherlands. Hi, Janek.
Hi, Kevin. Thanks for inviting me, and very happy to see you back after quite a while.
Yeah, we know each other from Dortmund University. There you did also some catalysis research, and what brought you to Twente now?
Yeah, as you said, my very early starts of catalysis research started at the Technical University of Dortmund, actually under supervision of you. So in my bachelor thesis, when I did my first research project, I designed ligands for homogeneous catalysis. I moved on to Leiden University, and that's a university in the Netherlands, and I did my Erasmus Plus abroad semester there, and I really fell in love to the Netherlands. So for me, it was pretty clear that after my master's, I wanted to go back to the Netherlands, and I found this PhD position there in the group of catalytic processes and materials at the University of Twente. So now about a bit more than 3 years ago, I started there my research, and now I'm working on catalysis there.
Interesting. Yeah, the Netherlands are a nice country. Also, when it comes to research, some of my friends also study there, and I've heard good things about the universities there. So now let's talk a bit about your research and the application. So as you said, catalysis now, what is the reaction you are looking at?
I'm currently working on the nitrate and nitrite reduction reaction. That's a liquid phase reaction. So we treat nitrates and nitrites that are dissolved in water, and we reduce them with using hydrogen on a heterogeneous catalyst. So we have a multi-phase reaction system that aims for the removal of nitrate and nitrite species from wastewaters, for instance.
Mm-hmm. And where do these wastewaters come from?
There's actually multiple sources that you can think of. The most prominent source is probably of waters from agriculture. So if you think about fertilizer use, we have many nitrogen components that on the one hand side are very helpful because they can be used as fertilizers and therefore increase the productivity of agriculture. But on the other hand, if we don't manage them properly, that leads to a nitrogen cycle that becomes increasingly imbalanced, and that can in consequence then lead to eutrophication of surface waters or can threaten the biodiversity, can also lead to health issues if we have them in our drinking water. But you could also think of industrial processes that have nitrates or nitrites in their waste streams.
Yeah, I think in agriculture context, like this over fertilization really is a thing that also some rivers are basically getting a lot of pollution from too much fertilizer use, which kind of feeds all the people around, but also then, has then some negative side effects. And another source that you mentioned when we talked before were from shipping. So there you are also in a research project. Maybe tell me a bit about that.
Yes, exactly. The project we are in is called LNG Zero, and we actually look into how we can make the after treatment system of cargo ships, or in general very big ships, like not the small ferries or so, but really big ships that ship containers from one end of the world to the other end of the world, and think of how can we make them more sustainable. And this is a project that aims for the use of LNG, so liquefied natural gas, as fuel. And that has first of all advantages that the direct burning of LNG has less or fewer carbon dioxide emissions than what is currently mostly used. That would be maritime diesel oil.
That's usually like the waste of the refinery, right? Like whatever is not used and other fuels that they can just burn in these giant ship motors.
Yeah, pretty much. And as you said, that's really like when I first saw the figures and all the data, these ship engines are really, very huge.
Yeah.
So it's very difficult to imagine how that really looks like. But yeah, in the end, the idea is if we use LNG, that we just by switching the fuel can already make the exhaust way cleaner. On the other hand, we still have emissions, but we, as the name says, LNG zero, then aim for zero emission. And therefore, we have multiple process steps. And at the University of Twente, we have actually 3 different PhD projects and one postdoc working on that project. And that's a consortium consisting of a couple of industry partners, but also TNO, that's the Research Institute of the Netherlands for Applied Research. And that project has actually 4 different steps that are first the methane oxidation. So whenever you think of methane or a combustion, there is probably incomplete combustions,
Okay.
and that leaves a methane slip. And these methane slip, as you may know, methane has a higher global warming potential than carbon dioxide, so you really want to prevent that. And one of my colleagues, Martin Chiquete Politicano, is developing the catalyst for this process step in order to convert the methane into carbon dioxide.
So that's in the exhaust where there's still some methane left, and then he's researching on a catalyst that basically burns all the leftover methane and then has less emissions or less greenhouse gas potential because CO2 is less than methane.
Yes, exactly.
Okay.
So you could think of, we have a very horrible greenhouse gas, methane, and we convert it to a less horrible greenhouse gas, namely CO2. And we actually don't stop there, but we also want to take this carbon dioxide out of the exhaust stream by doing carbon capture. In general, there is already a lot of research going on to capture carbon dioxide, be it from point sources such as exhaust gases, as we do, or via direct air capture. And we also want to do this carbon capture on the ship. So we want to store the captured carbon dioxide on the ship, and then we can unload that on a port and pump it into ground, or we can also use that as a resource and make new LNG from this carbon dioxide. But the last step, like the utilization of the carbon dioxide, is beyond this project. But what we do is that we want to capture the carbon dioxide from the exhaust stream on the ship to gain this net emissions. And then the next process step would be the NOx removal, because whenever you have a combustion process, you will have NOx emissions, and you can, in the so-called scrubbing process, remove these NOx emissions by just washing them out with water. And then you can transfer the NOx gases into nitrates and nitrites that are dissolved in water. And as you remember what my research is about, then my process step comes into play, because we then try to remove these nitrates and nitrites in a catalytic reactor and form nitrogen, which would then be harmless.
Yeah, nitrogen is already a lot of the air, so yeah, that's not really a problem. And how would they usually do this process step? So if you want to reduce the emissions from that, how's the state of the art right now?
As far as I know, there is mainly 2 technologies. That's on the one hand the scrubbing that we use in different ways. The alternative would be selective catalytic reduction. So that would be a gas phase process where the NOx gases are then also reduced to nitrogen, mostly with the help of either urea or ammonia. That would be, let's say, the state of the art in the gas phase. Or in liquid phase systems, we have scrubbing. In scrubbing, there's different approaches. But the key point is that most of the times the scrubbing brine is just discarded to the sea. So we don't treat them further, but just throw them into the ocean.
Yeah, dilution will do its job or something.
Yeah, that's the thing. And what's the main problem there is also that there is very little registration. Like if you think of the high sea, there doesn't exist too much law, right? Who would check that? How would you check that? And therefore, the economically most feasible option is, of course, just dumping it.
Yeah, but that has a negative track record. I think back in the days, they also had a lot of sulfur waste from the chemical industry, and they also just loaded that on ships and dumped it into the sea, and that led to, especially in the North and East Sea, to drop in pH, which was then really a problem. And I think also in these more confined seas, a lot of nitrate would also, probably lead to more algae and stuff like that, right?
Yeah, true. If you discard, as you said, it's a matter of concentration. But if you just dump enough, then also you will have the eutrophication problem, that you grow more algae, that you reduce the amount of oxygen, and then at some point the water might tip over.
Yeah.
Acidification is also a problem. So if you scrub, the pH typically of these brines is decreased. So the pH of the ocean would also decrease over time.
Yeah. I think for the high sea, it's probably not, at least for a short time, not that much of a problem. But yeah, close to the coast, where there's less mixture and less water to mix with, it might cause more problems. Also in the ecosystems over there. Quick break. Thank you very much for listening to the show. I would like to ask a small favor from you. Please hit the follow button and leave a review on wherever you are listening. This really helps me and costs nothing to you. Thank you very much for your time. Back to the episode. How is your reaction now set up that you can remove those nitrates and nitrites?
Yeah, so what we basically use, or let's say in our fundamental research, we typically just have nitrates or nitrites dissolved. We prepare our catalyst, and then we either use a semi-batch reactor, that would be then a liquid phase reactor with continuous gas flow, and the gas flow is then consisting of hydrogen as reducing agent and carbon dioxide as buffering agent, because the pH of this reaction would increase, so we consume protons in order to reduce the nitrates and nitrites to nitrogen, and in order to fundamentally understand the reaction, we try to keep the pH constant, and then we try to improve the catalyst. We try to have a look on the reaction kinetics to better understand the reaction. And my particular research focus is the preparation of bimetallic catalysts. In our group, we previously did a lot of research on nitrite reduction reaction, so NO2 minus reduction reaction, and that is typically done in palladium catalyzed systems. However, if you use nitrate, NO3 minus, you do need a second metal that promotes the first reaction step from nitrates to nitrites. And I'm playing around with tin. There is also other options, namely indium or copper, and they are, let's say, all similar. Tin and copper are the most used ones, also because of the availability of tin and copper. Tin is a bit more active than copper, and until now a bit less investigated, so that's why we chose for tin. And the research grab I found at the beginning is that you have a quite diverse landscape of researchers looking at the reaction from the engineering perspective, from catalysis perspective, from environmental perspective, and that leads to very different approaches, and sometimes also, let's say, interesting catalyst formulations.
Okay. How?
Yeah, let's say there's many ways on how to prepare catalysts, and the easiest one you can think of is just wet impregnation. So if you think of a porous support material that hosts the metal, you would impregnate them with a precursor solution and evaporate or filter off the mother liquor, that you in the end have your solid support particle with the catalyst precursor. And if you do that with two metals, and you do that without any control, the metals will be all over the place. So there's probably no preferential deposition of the two metals.
Okay.
On the other hand, the reaction mechanism tells us that in the nitrate reduction reaction, the two metals, in my case palladium and tin, do need to have contact to do the job. So the tin reduces the nitrate to nitrite, but it needs the palladium to be recovered. So in catalysis, we always want to have a closed catalytic cycle, and the tin itself cannot close, is not self-sustained, like it needs the palladium to be reduced. And if it's then in the absence of palladium, that tin wouldn't do anything. So we really need this close proximity.
So it would just be normal non-catalytic reaction where the tin is used up and then it would stop and you would basically need quantitative amounts of tin to perform this reaction.
Yeah, yes, indeed. In the extreme case, yes. Of course, if you do this sequential impregnation, statistically you will also have some proximity between tin and palladium, but that's far from being optimized. And if you really want to understand what's going on, you better want to have them in close contact, and at least you want to know what's happening. And what we tried and investigated in the last couple of years is so-called controlled surface deposition. So we try to deposit the tin selectively onto the palladium. And we found out quite interesting trends already. So the deposition behavior, for instance, depends highly on the support material. But most importantly, that the amount of tin you need on this palladium is significantly less than what all people do in literature. So if they use bulk ratios, let's say based on weight percent, half tin, so 1:2 ratio tin to palladium or so, that would be way too much if you prepare the catalyst in a controlled way. And that's, let's say, the main advancement we see, that we need only very little tin if that's well deposited on the palladium.
Because probably when you do this random approach, you also get a lot of tin without palladium contact. And those would perform the reaction just once, although there might be a lot of active sites in the first place, but then they could not regenerate, right?
Exactly, that is the case. So you would underutilize the potential of your metal. And the second advantage of these materials is that we have still quite some palladium available. So we have then the tin mainly on the palladium or in the subsurface of the palladium. And that leaves also quite some palladium open for the nitrite reduction reaction. So what we see is that these catalysts have very similar activity on the nitrite reduction reaction, so the second reaction step, as the bare palladium catalyst. And if you think about a process later on where you would like to convert both materials, both reagents, nitrates and nitrites, that's highly beneficial to have a catalyst that does the first reaction step, but with the second reaction step is not substantially slower than with bare palladium catalyst.
Oh, okay. Yeah, that's also good news if you want to have this tandem reaction, I think you could call it also, right? That you have both
kind of
reactions, and then if there's a bottleneck in between, that would basically destroy the whole performance.
Yes, indeed. Our common past with tandem catalysis is somehow comparable. It's a bit different. So if you really want to have a look at the fundamentals, I think tandem catalysis, if I remember correctly, you would have the same active site doing the job for all reactions.
Yeah, with one catalyst doing all the reactions, and you don't have to add anything. That's then auto tandem catalysis, and with two different precursors, it can be orthogonal tandem catalysis, and I think that might be the case here.
But yeah, indeed, if you zoom out a bit, we have essentially two reactions running at the same time with one catalyst material that hosts then activities for both reactions. Yeah. And that's pretty cool.
Yeah, definitely. From a catalyst design perspective, that's definitely also a challenge, but has huge potential because you don't need two reaction steps. In theory, you could probably also do the reaction in two steps with two reactors, or is this not possible?
That's a good question. Well, it would be challenging. Let's say the second reaction step you could easily do in a second reactor. The problem is that the second reaction step is typically faster than the first one. So if we want to go from nitrates to nitrites, that is in the overall process the rate determining step. And then once you have the nitrites, they are quite quickly converted to nitrogen. And that is also one of the big fundamental problems in these reactions, because if you have a slow supply of NO2 minus, you will have relatively high hydrogen to nitrogen ratios on your catalyst. And the main issue of this reaction is the selectivity towards ammonia. And if you have high hydrogen to nitrogen ratios, the likelihood to form ammonia is higher.
Okay, and ammonia you want to prevent.
Yes, you could of course think of, hey, ammonia, there's also a lot of research on ammonia. Why don't we want to make ammonia? But the typical concentrations we use are 50 milligrams per liter, maybe 100 milligrams per liter.
Yeah.
So it's very, very low. And if you really want to make value products out of that, then you will have a difficult life in isolating these and then in the end selling them. And if we think of ammonia,
That's a huge process.
it has some value, yeah, but the scale of these processes is so big. So I'm not let's say my background is chemistry and I'm not an expert in techno-economics, but I think you don't have to be an expert to realize that it's probably not so sensible to convert 50 milligrams per liter into ammonia, which is also not super expensive. So,
yeah, definitely.
We rather want to produce nitrogen and therefore reduce the environmental impact of these pollutants.
Definitely. Maybe let's also go back shortly to your setup. When you use gaseous hydrogen as the reducing agent and you have your liquid brine and you contact all of them with your catalyst, how do you do the contact between gas and liquid? You probably dissolve it.
Yes, actually that's a relatively easy setup. It's a semi-batch reactor, so you can think of a 1 liter glass vessel, and then we put there some liquid, typically 300 milliliters, and we continuously feed the gas mixture. We steer that quite vigorously, so mass transport is also a big issue, or like it's not necessarily an issue, but something you have to think about, because you have the transfer from gas phase to liquid phase and then from liquid phase to the solid, and you have a porous material, so you might also have internal mass transfer limitations. And especially since this reaction is relatively fast, so it runs at room temperature, you really have to take care that your particle, the catalyst particles, are small enough, that the diffusion lengths are relatively small, and that you check that carefully to really measuring the kinetics, and that you're not only measuring the mass transfer. There's also, I'm pretty sure, many papers that just report physical phenomena.
Yeah, definitely.
Nothing wrong with physical phenomena, but if you want to do kinetics on that, then you better check that.
Yeah, definitely. You always have to keep that in mind when designing the experiment, that you actually get the question answered you asked and not something completely different, which might look like your answer.
Yes, exactly. And then essentially we have the liquid constantly saturated at a certain hydrogen partial pressure at ambient conditions, and then we take samples over time. We analyze them with ion chromatography. So that is a technique that allows us to detect nitrate, nitrite, and ammonia. And there is also one big issue in this reaction, or in the entire research field, that many people, or actually all people except one single paper, don't physically close the mass balance.
Okay.
So we convert nitrates and nitrites, and we detect then the nitrates and nitrites and the ammonia, but we don't detect the nitrogen. And that has a couple of quite good reasons, because it's super challenging to do so. We have, as you just heard, we have a liquid phase and a gas phase, and if you want to sample the gas phase and the liquid phase, there will always be a delay. Even if you can make your entire system super inert and suppress all nitrogen contamination from the outside, which is also a huge challenge, you would still have a delay between the gas phase and the liquid phase. And to then match these data points is super difficult. So to achieve a close mass balance is close to impossible. There's one paper published, they did that, but they also used isotope labeled nitrogen species. So you can think of a research on its own just to close the mass balance. So at some point, the entire scientific community in that field agreed that the only products, or the only significant products, are ammonia and nitrogen, and we can just make the balance based on nitrate, nitrite, and ammonia, and assume the remaining part.
Yeah, just assume that everything that you not detect is nitrogen.
Exactly.
Yeah. So I would also imagine that when you want to analyze the nitrogen, some of it would also be still dissolved and not completely bubble out. And then, yeah, that's very complicated.
Definitely, the dissolution equilibria will also make your life very, very difficult. So as I said, it's quite good reasons that you accept that just because you cannot really do better, or it's almost impossible to do better.
No. And then how did you look at this problem? I mean, when you say that no one really did it, but sounds like you did, try to close the mass balance.
Well, we actually didn't try, but we observed something very, very odd. Because we were running a reaction and we were running then beyond full conversion. So at some point we saw, okay, all the nitrates and nitrites are converted. We formed some ammonia as we would expect. But when we had a closer look, we saw that there is still ammonia formation after full nitrate and nitrite conversion. And that can, of course, not be the case, because it cannot come from nowhere. And then we were first doing some calculations. Okay, how much accessible metal area do we have? Is there maybe still some nitrogen species that sit and chill on the metal forever? But we could very quickly find out that that cannot be it. So there must be some kind of nitrogen reservoir in the reaction system that is slowly converted to ammonia. And then we sat together and thought, okay, what could that be? Developed a couple of trapping strategies. And in the end, we found out that there is hydroxyl amine as reaction intermediate. And depending on the conditions and the catalyst, that can already be quite a bit. So 10% selectivity is not a surprise. And in some catalysts, we even found up to 50% intermediary yield. So it's actually a substantial amount that is hydroxyl amine.
So that's basically the partial hydrogenation product of this reaction. Or how does it happen?
Exactly. How does it happen? That's of course a very, very good question. We are currently investigating that a bit deeper. So recently published one paper that is more focused on the phenomenological approach. So a bit of a shout out to everyone working in the field that we maybe have to have a bit of a closer look. So we just tested a bunch of different reaction conditions, a couple of different catalysts, and proved that whatever we do, we always see hydroxyl amine. Because if you find something that is not being observed for quite a while as a PhD in the middle of a research trajectory, you also first, of course, questioning yourself. But I can say that we really did our best to prove ourselves wrong, but we couldn't. So apparently we're right. And we are now trying to a bit more structurally, a bit more systematically investigate that reaction with just one catalyst and with a bunch of different reaction conditions, and then try to get a bit of an idea how the reaction mechanism indeed goes. And what we think is happening is that we have hydroxyl amine, so adsorbed on the surface, and that's also, if you look at the reaction mechanisms that are published, it's sometimes mentioned, but it's never mentioned desorbed. So if you think about that a bit more detailed, you would think of different nitrogen species adsorbed on the metal catalyst, and then you would always have we call that microkinetic modeling, step by step add an atom or add an electron, spit of water, for instance, and then there is species that look like NOH, something in that terms, and that can then easily be converted to hydroxyl amine. And apparently it does desorb from the catalyst surface, and that is the thing that was up until now not really considered.
Yeah, that's interesting, because I don't know exactly how it works for the heterogeneous catalyst, but for the homogeneous catalyst you could do a lot of like NMR, IR, and different kinds of analysis to figure out how exactly the reaction works and what intermediates you have. You can trap some intermediates with very low temperatures and then get a spectrum of them and know exactly how those intermediates look like. But how would you do that for the heterogeneous catalyst?
In heterogeneous catalysis, or in general in that reaction systems, it's quite challenging to do characterization. What we actually did in the past, and with we I now mean our research group in the past, did ATR-IR spectroscopy. So that is an infrared spectroscopy technique where you coat your catalyst on a rod or on a crystal, and through these crystal, the IR beam is sent, and you can think about it like in a glass fiber cable. The IR beam bounces out of these crystal for a tiny little bit, let's say a couple of micrometers, and that can then probe the molecules adsorbed on the surface. It of course also probes the liquid bulk, but also the molecules adsorbed on the surface. However, IR, you probably also know that you can get an idea of the structures, but it's very difficult to distinguish between the exact molecules. So if you then think about different NOH species, you cannot really tell, is there now one H, is there two H's, how does that exactly look like? At the same time, you must realize that the spectra is incredibly noisy. You have the liquid background, you have very low catalyst, like metal loading on the catalyst typically. The concentrations are typically very low. So in the past, it was proven that there is some NHO or NOH species, but to really nail down what's the species wasn't really possible. But that's also part of my research right now. Based on this finding, I revisited a couple of publications and particularly questions, okay, have we overseen something there? Because for instance, in one of the papers, we also reported N species, so just one nitrogen atom adsorbed in the surface, and that you would never see in IR, because that is a species that is not IR active. You don't have a dipole moment, so you cannot detect that. And back in the days, they were also observed that ammonia was formed after full conversion, but the amounts were just much lower, and then they could close the mass balance, let's say, or they could assign or could correlate the ammonia amount produced to nitrogen species on the surface. On the catalyst surface. So they were assuming, okay, probably there are some spectator atoms that if you just wait long enough, go from the spectator role and are converted to ammonia. And that made total sense back in the days, but if I look at that from a perspective right now, it might also very well be that there was some hydroxylamine
formed
in the reaction mixture.
What did you different to observe this hydroxylamine now compared to those older measurements?
So what we do to detect the hydroxylamine is we derivatize the hydroxylamine into an oxime. So when you think of the semi-batch reactor, we take samples over time, and these samples we immediately after the sampling add a tiny droplet of benzaldehyde. And these benzaldehyde is then doing oxidation reactions. It's thermodynamically way downhill, so it happens naturally within, the concentrations are used less than half an hour. And then I have an oxime that is relatively stable and that we can detect with HPLC due to the UV-vis absorption of the benzaldehyde. So the benzaldehyde oxime is then also UV-vis active, and we can easily detect that with HPLC.
Yeah, interesting. On the other way around is also that hydroxylamine is used to detect some aldehydes, and you then use the oximes to quantify them. It's also used the other way around.
Okay, that is I was not even aware of.
In some, because the aldehydes are much more volatile than the oximes, you can basically trap them also as the oxime and then use liquid chromatography to detect them. It's because it is a really fast reaction and it's almost always quantitative. So you use it the other way around.
Yeah, in essence, it's the same thinking, right? Like we were suspecting something, but we couldn't really detect that. So we were trying to find some vehicle that converts the hydroxylamine into something that we can detect.
Yeah.
And then we could relatively quickly establish the characterization technique. And I was actually at a conference not too long ago at the North American Catalysis meeting in Atlanta and was presenting this work as well. And there were already a couple of people actually working on hydroxylamine. And they were complaining on how difficult it is to properly detect and quantify hydroxylamine. So we are now also in contact and then see whether they can also apply this strategy for their own research.
Interesting. So you could already, with your research, help others to improve on their analysis, and then hopefully there will be new discoveries in this field which will basically drive this reaction towards the usable applications.
Yeah, let's see. At least I could give some inspiration for new approaches for them as well. Whether it's then in the end works out, that's on a different page. I recall someone from the US, and they wanted to work in gas phase, and then it's probably a bit different. But at least he has never thought about that way, and he was inspired by that, and he also wanted to try that out.
Interesting.
Apparently, that is something that might also help other people from the field.
Yeah, especially when it was overlooked by everyone for quite a while. That might also, previous researchers might then revisit their questions and look if they might have missed something, and then could improve the whole reaction.
It's definitely, when I was explaining that the first time at the conference, let's say I was a bit more excited than on a normal talk, because you never know how the feedback is. Because it's something that has some more potential for criticism or for very critical questions than if you have your standard talk.
Definitely. But those help.
Yeah, definitely.
Because when you have critical questions, there's might be something you have missed, and then you would also profit from that.
But as far as I know, luckily there was only positive words and, let's say, agreement that we might made our life a bit too easy.
In what way?
And I'm curious what's to come. Yeah, that we just assume that the mass balance, that we don't close the mass balance, that there was agreement like, yeah, I mean, you're right, we never really checked that. Maybe we should have.
Yeah.
And now I'm actually quite curious what, let's say in a year or two from now, it takes always quite a while until in research, if you now publish, we published the paper, I think about 1.5 months ago. Follow-ups on that will probably take a year, maybe 2. So exciting.
Yeah, because all these tests have to be done first, and then you can go into discussion with those people. And now with all these findings, and then you can basically improve this whole catalyst and get a more efficient reaction. What would be the applications for this improved process?
I'd see that in 2 different ways. First of all, the way in which that reaction is mainly researched about, so that's drinking water purification. And for that field, the hydroxylamine finding is quite challenging, because hydroxylamine is even more toxic than ammonia and harmful for water environment. So if you look at the safety data sheet, it basically has everything you don't want to have in your drinking water. So with that regard, I'd see quite a setback. If we think of the process we are researching for the exhaust gas catalysis of big ship engines, I think that wouldn't be a huge issue, because due to some process integration challenges, we need to have a closed loop system there anyway. And what we also showed is that this hydroxylamine is just an intermediate, so it's not a final product, it's further converted into ammonia and nitrogen. So it's not ideal that we convert it further to ammonia, but we don't have the hydroxylamine if we just let the reaction run long enough.
So that's just a reaction engineering problem and not really a intrinsic problem of the reaction.
Regarding hydroxylamine, probably. The intrinsic chemical problem is that we still have ammonia. So if you think back of the process for the exhaust gas catalysis, if you then have a closed loop and you constantly form ammonia, then at some point you will have a relatively high ammonia concentration in your liquid that you don't want to have on a ship, or generally you have to have a bleed at some point. But that is something that you might be able to work around. But if you think about drinking water purification, you will have higher ammonia concentrations than you thought initially of, and that is the main problem right now anyway. So there I really see challenges how we can make that work. I think that we would also then need some engineering help, some engineering solution that you use the nitrate-nitrite reduction reaction to convert the majority and then do the last tiny bit with membrane techniques, so reverse osmosis or other techniques that can really do the last tiny bit of the cleanup.
Yeah, I think that's also a concentration problem, but when you think of like a chemical plant, if you think of the wastewater of a chemical park and you have some chemical plant that have a lot of nitrates or nitrites in their wastewater.
Okay, then you could certainly think of using catalytic hydrogenation of these compounds to form some nitrogen or to remove these nitrates and nitrites. Because then that is a similar case than on the cargo ships. You probably won't use that water as drinking water anyway, but you can reduce the waste load substantially. So even if you cannot reach the goals for the ammonia limits for drinking water, you can still remove the predominant share of contaminations, and therefore are way better than just having the highly concentrated brines. Because let's face it, if you do, for instance, reverse osmosis for water purification, you still end up with a waste brine.
Yeah.
So in that sense, you do have achieved your goal, you do have clean drinking water, but on the other hand, you have a other problem, namely the waste brine. And that's also something...
Could you feed that back into your reaction and then basically just have this concentrated brine again from the reverse osmosis and then slowly convert everything to nitrogen?
Yes, that's actually the idea also for the process on the ship we have. So we we will do the pilot testing actually the end of this year. But what we are thinking of is that we convert as much in our catalytic reactor as we scrub from the exhaust gas. So you have a steady state operation. Let's say you have a relatively enriched nitrate and nitrite concentration. But whatever you add in the scrubbing process, you convert in the catalytic reactor. That also helps you, if we go back to the fundamentals, having a high nitrogen selectivity requires high nitrogen to hydrogen ratios. So if you have higher concentration, the likelihood to form nitrogen instead of ammonia is higher. So we can use some process engineering there to hopefully maximize the nitrogen yield. And since we don't need to drink that water, we can just operate at a steady state between these two processes to keep the nitrogen content high enough to prevent ammonia formation, and we don't have to go to full conversions.
So at least dropping the amount of pollution by the highest amount possible, and then it's not drinking water quality, but it still reduces a lot of the emissions.
Exactly. So then the goal in that sense would be waste reduction and not drinking water supply.
Yeah, definitely. But that's also then just a different question you have, and you want to go in that direction. And then, it might fit. And for other processes, they are already, for drinking water, we have the biological processes, which are really good in also removing those nitrogen compounds for drinking water treatment.
Yeah, indeed. In general, for drinking water treatment, there is different processes that also work. They sometimes have, if you for instance think about reverse osmosis, you need a lot of pumps and have quite high energy demand. If you think about microbiological treatment, you always need some carbon, and sometimes the drinking waters or the waters are already too clean for that.
And a lot of space too that you don't really have on a ship.
Space. Indeed. Well, space is also a challenge for us. It's also one of the major challenges, that the liquid volumes we need to treat are huge, but ships are also huge. So let's see whether we can make that work. But the process integration is the main challenges we have and the main things we think about. But let's say the scrubbing was also earlier not really optimized, because if you just dump everything into the sea, then volume is not really a critical point. So you just put more and more. But now that we think about it, there was also some advancements by TNO, by our collaborators, that they could reduce the liquid volumes quite substantially. So let's see where we end up, whether that is competitive to the existing technologies.
Yeah, but that's where the improved catalyst comes into play, with a better catalyst and then with a higher time space here, you need a smaller reactor for the same conversion.
Yeah, exactly. So in our consortium, there is also ship constructors and ship owners. So it's actually from a personal development perspective, super interesting on how all these things work. So that's things you in your chemistry study you probably have never thought about, but then out of a sudden you also have to think about, okay, maybe hydrogen storage on a ship is not so easy. So is that something that we can solve? And then we can think with all the other people, okay, we might be able to put a small electrolyzer on your ship to make the hydrogen on site. And then you all of a sudden end up Googling, is there container size electrolyzers that can supply sufficient hydrogen? And that's probably things, if you asked me at the very beginning, I would never have thought about that is then also part of my job.
Yeah.
It's of course also only small part, and the main part is still the catalyst development, the catalyst testing and characterization. But it's quite interesting to have an horizon where things potentially can end up if everything went well.
Yeah, definitely. That's why I also like this applied chemistry a lot. It's very interdisciplinary. You have to work with engineers. You have to work with also different parts of engineering, and in the end, go towards a product that works and people actually can use and also can use economically. That you also have to then take also this whole economic side into mind. It's really interesting to have these really complicated problems then that you can solve with all different disciplines together.
Yeah, I'd say for the technical economical analysis, that's maybe a bit too early. So
Yeah.
I'd say the project we have aims for tier L4, so technology readiness level 4. That means that we want to demonstrate in the lab that this technology has potential. Whether it's then competitive to the things we have on economic basis, that's then probably a couple of more PhDs on its own. But still, we have some idea of how that process or how we can transfer our fundamental research into something that might be able to be used in the very long run.
Yeah, very interesting research. And now to the last question for today's episode. What is your favorite discovery in chemistry?
That's actually a quite difficult question. I have never really thought about the main discovery. I mean, I'm working in nitrogen chemistry, so probably Haber-Bosch is a quite obvious call. And of course, it causes some problems with the eutrophication and the imbalanced nitrogen cycle. But on the other hand, we would probably not be able to feed the entire global population without it.
Yeah, definitely. So, that's actually also my favorite discovery, the Haber-Bosch process. And it basically feeds almost half of the world's population without all these synthetic fertilizers. It would not possible to feed all these people. And so that's really crucial for humanity, I think.
Yeah, I absolutely agree on that.
Okay, then, thank you very much for this nice insights into your research.
Thanks for having me.
Also, thank you very much for listening. If you like this episode, then please leave a review on wherever you're listening. Also, click the follow button. That really helps the show to grow. And if you want to be part of a future episode, reach out. Either find me on LinkedIn or send an email to contact@innovateandreact.com. And until next time, keep innovating and stay curious.